dive into real-world applications and how we can use differentiation to solve them, we need to pause and talk about implicit differentiation, what it is, and how to do it, because we're going to need it for these real-world problems. If we look at the next differentiation question, it's a straightforward one we can handle easily. But let's focus on the notation they asked for, because you really need this to understand implicit differentiation. They asked for dy over dx. In one of our first differentiation videos on notation, we said this notation tells us exactly what to do. Quick recap. The part on top, dy, tells us what the equation should look like before we differentiate. In other words, which variable should be the subject. In this problem, the subject must be y, so we should rewrite the equation in the form y equals something. The letter on the bottom, dx, tells us which variable we are differentiating with respect to, in this case, x. So this was just a standard differentiation problem. Now what do we do if they ask for dx over dy for the same equation? Looking at the notation, x is now on the top of the fraction, which means we must rewrite the equation so that x is the subject. In other words, x must stand alone. Once we do that, we get the following form. Next, look at the bottom of the fraction. It's y, so that's the variable we differentiate with respect to. When we differentiate with respect to y, we obtain the result. But what happens if we can't rearrange the equation so that the variable we want as the subject stands on its own? Let's look at the next example. In this example, they ask us for dy over dx, which means we need to make y the subject of the equation, get y on its own, and then differentiate with respect to x. But if we take this equation and try to isolate y using ordinary algebra, we find it isn't possible to get y alone. So what do we do? This is exactly where implicit differentiation comes in. One of its key uses is that it lets us differentiate even when we can't solve the equation to make the subject stand alone, as in this case. All right, let's see how it works. We've already seen that we can't make y the subject in this problem to differentiate in the usual way, so we'll use implicit differentiation. How does it work? We start by placing the differentiation operator on both sides. Say d over dx, acting on the left side and on the right side. And then we differentiate both sides at the same time using our familiar game plan. Step 1 of the game plan is split up. Split each side at the plus and minus signs that are not inside parentheses, radicals, fractions, or exponents. After we split, we get the following. In the second step of our differentiation game plan, setup, remember we are not differentiating yet. We're only laying out the structure according to our table. If this table doesn't look familiar, go watch the full video on how the differentiation game plan works. Otherwise, you'll get lost here. What's absolutely crucial now is how we handle the y parts, because this is new compared to what we've done so far. You must remember that y represents our function we're differentiating. In other words, y contains x's, so we need to set it up so that it will also be differentiated in the next step. The rule in step 2 is treat every y as if it were an x. This is extremely important. It's the make or break idea. Everywhere you see a y, act as though it's an x. With that in mind, we can use our table to do the setup. In the first term, we can see there are two x-like factors being multiplied, so the structure we need to set up is the product structure. When we implement that structure, we get the following result. In the second term, there is only a single x, so no special structure is needed. We just carry it across. We can also see that the third and final term also has only a single x, so it doesn't need any structure either. We carry it across as well. In the third step of our game plan, we actually differentiate, and this is where we use the cupcake method to decide whether each piece is a simple function or a composite function. When we just have ordinary letters with no brackets raised to a power, we use the circle trick of ordinary differentiation. But when something is inside brackets and raised to a power, we use the chain rule. Now, what about the y terms? Remember, the reason we use the chain rule is that a bracket raised to a power hides x's inside, like a cupcake with a hidden center. And when we differentiate, that hidden center must also be differentiated. The same idea applies to y. Y represents a function of x, so it also hides x's inside. That means in implicit differentiation, anytime you differentiate a y, you must use the chain rule. This is crucial. So let's differentiate. The first term is a simple function. No brackets to a power, so it gets ordinary differentiation. The second term contains y, and a y always triggers the chain rule. Bring the exponent out in front if there is one. Keep the bracket with y exactly as it is, and then multiply by the derivative of the inside, meaning the derivative of y, which we say as dy over dx. The next term also has a y, so we repeat the same chain rule process. The last two terms are again simple functions, so we handle them with the circle trick of ordinary differentiation. After differentiating everything that needs it, you'll notice we now have dy over dx terms in the result. The final step of implicit differentiation is to make dy over dx stand alone. We do that by factoring it out wherever it appears, then isolating it. And that's it. We've differentiated implicitly. Well done. To sum up implicit differentiation, use it when you can't make the subject stand alone. For example, when you can't isolate y. The method is, take the equation exactly as it is and differentiate the left and right sides. You still follow the usual differentiation game plan. Step 1. Split up. Nothing changes here. Split the expression at plus and minus signs that aren't inside brackets, roots, fractions, or exponents. Step 2. Set up. Now we suddenly have y terms. In this step, treat every y as if it were an x and use your standard setup table to choose the correct structures. Step 3. Differentiate. The key idea, whenever a y gets differentiated, use the chain rule. Remember, y represents a function of x, so there are hidden x's inside, like a cupcake with a surprise center, and that hidden part must also be differentiated. Final step, isolate the result. Use ordinary algebra to make dy over dx stand alone. That's it, you've differentiated implicitly. Crucial reminder, the differentiation process itself hasn't changed. It follows the same game plan as always. Make sure you understand that game plan. Revisit the video if needed. Rewatch this lesson, try the problem yourself, and you'll see that implicit differentiation, though it might feel intimidating now, quickly becomes manageable and unlocks real-world applications, which we'll start next. In my ebook course, implicit differentiation is neatly summarized with another worked example to help you cement the process. Winging calculus is like winging a parachute jump, fun until the ground shows up. Ditch the 30 open YouTube tabs at 2 a.m. trying to integrate and grab my ebook course, step-by-step fixes and shortcuts. Cheaper than your monthly coffee bill and way easier than explaining a flatlining GPA. Course link in the description. If this helped, smash like and subscribe. See you next time. Cheers!